In this video, we're going to be showing you how to verify and how to calibrate the JF-1A inline sensor in the field using the D-2 calibration kit that we are selling, which includes two 24-volt power supplies, calibrated voltmeter, calibrated temp probe, JF-1A test cables and wires for the power supplies, a JF-1A ST stick handheld meter, and the JF-1A STVC SEF calibration box, or the JF-1A STVC USB, which is a calibration device shown in this video. Thank you for watching, and throughout this video you'll see how this kit, along with your own equipment such as a temp bath, can be used to calibrate the JF-1A for temperature and for conductivity in the field using NICS traceable standards. The first step in this process is to prepare your fuel samples using a clay filter, which comes as part of the kit. You will get the clay.
To create zero fuel, the first thing we do is open up our fuel cabinet. Inside we have our sample bottles, and we have some Jet A fuel in a 55-gallon drum, which we're going to put into our glass jars with our outboard pump. Once those are full, we'll take them over to our clay filter. Here I have a completely clean jar that's been cleaned with isopropyl alcohol and heptane and then air dried out, and now it's completely clean and ready for filtered clay fuel. And that goes underneath the filter stand there. If I zoom out, we have a large glass tube right here that goes down into the glass bottle, and within that is this clay.
The clay we use is Attapulgis clay. It comes from clay treater cartridges, and we use it to filter the kerosene. This makes the kerosene into very low conductivity jet fuel, as it removes all of the surfactants and other things in the fuel that raises the conductivity, making the fuel very clean.
What we do is we pour the fuel into the top here, goes down, filters through the clay into the glass bottle, and then once that glass bottle's full, you have zero fuel, which is fuel that is somewhere around 0 to 10 picosiemens per meter. You can see the fuel now seeping down through the clay. I leave the bottle up there so it drains out all the way. We keep a chart every time we change the clay, which I just did. You mark down the date, and then for every bottle that you run, you mark it once. I've seen the clay averages with this amount of clay. Averages about 6 bottles before it gets saturated and needs to be changed out. So that's what I've seen. Individual results may vary on that, however that's how it works. And then once I open up the spigot here, you'll see the fuel will start to come out. Now it'll fly down through the clay. And as it goes through the clay, it's filtering out all the stuff that's in the fuel, so it comes out extremely clean, which is why the conductivity is near zero. So after about 15 minutes on our setup, the fuel will filter all the way down into the other sample jar, and you can see here it looks extremely clear. And when it tests out, it should test out to be about 0 to 10 picosiemens per meter, hopefully on the lower end of that scale. So we take that out of there, take our other sample jar off of here, and then we mark down that we have ran a sample jar. So there you go. And that's how we make a 0 sample and make sure that the clay is good. And then we end up with a nice 0 reference fluid.
The next step in the process is to set up your fuel lab, and I'll take you through how you do that now.
Welcome to a video where I'm going to be showing you how to use this, the JF-1A ST handheld conductivity meter, a temperature bath with a handheld temperature probe, our USB calibration for the stick, which can also be replaced by the SEF box.
This is the preferred device that we will sell with the kits, which is the JF-1A ST VC SEF, which is a box that, as you can see, the stick handheld plugs into, and the box itself runs through the calibration process with a 2-button, very easy to use system, and can also run the verification process. And this doesn't require you to connect it to a computer, making it much easier to use, and you can use this to calibrate any JF-1A ST stick handheld in the field. And this box lasts for up to 10 years before the box itself needs to be recalibrated. So all you need is wall power and one of these boxes, and you can calibrate any of your stick handhelds in the field quite easily without having to use the software that we provide with the USB version of this device. So that's why this is the preferred version. However, we do not have one in stock because they're sold out because they're so popular. So make sure to order this option with the kit.
Our voltmeter and our inline conductivity sensor that we're going to recalibrate. So welcome to how to calibrate and verify a inline conductivity sensor in the field with the kit that we will sell you as part of the mobile calibration lab for the inline sensor. What you need as part of that is a stick handheld. You need either calibrator box SEF or this USB version. We recommend the SEF version. You need a computer that has the hyperterminal program on it. You need the 2 power supplies, 24 volt, that we will sell to you. You need one of these, which we'll sell to you as well, which is a calibrated voltage meter. And you need one of these, which is your inline sensor that you're going to be recalibrating. Okay. You also need a temperature bath, and in our temperature bath we use silicone, and we're selling you as part of the kit one of these Fluke temperature gauges that's calibrated, but you'll have to get that recalibrated annually. Okay. The last thing you need is crate treated kerosene, as I showed you how to make that with the clay treater that we're selling you the clay for. You just need to provide your own glass tube for that. And then you have the jet fuel that's got some SDA in it. And you have some diesel fuel that has a lot more SDA in it. This is your high-end value, your mid value, and your 0 value. And then this here is lab-grade isopropyl alcohol, which you use to clean the sensor and the handheld in between samples.
Now we will begin the initial board test to check the functionality of the sensor.
So when you first fire up hyperterminal, you want to create a connection, and what you'll do is you'll connect the sensor with the JF-1A test cable we'll give you, which is a USB to serial port test cable that you connect here at the 4-pin header on your JF-1A sensor. which can either be the black version like this or the green version that connects underneath. It'll come with the appropriate connection. Okay, and over here it connects into your USB terminal. Then you open up Hyper Terminal, which is a free program you can download for Windows. It just connects via the terminal program. And you want to open up a new connection, set it to the following: bits per second 9600, data bits 8, parity none, stop bits 1, flow control none. Hit OK. You can configure further settings if you want, like these. I tend to put on echo typed characters locally just to make it easier. Okay. Then you go over here and you connect, you pick the correct COM port, which for me is COM port 3. And then you go over here and hit connect, and it should be open. If it's in open mode, you can hit, or normally it would pop open in run mode, which is star R. It's already in run mode. Hit SC, it'll start taking data points. And in run mode, it gives you conductivity, temperature, and compensated conductivity. So that's the conductivity when adjusted for the temperature. Which it's in air, so 1.0 is about correct. These sensors generally read a few minus in air, just the way they're calibrated. You can see here it's running where it was before, 4 something volts. That's because the serial data is connected. Now, first thing we do is we take down the RCal information. Do that, you hit stop, hit O. Sorry, it's already in run mode. You hit RCal, which gives you the internal information stored in the instrument. So we'll take down all this information and write it down in our sheet here and fill out that information on the first page. It all comes from right there. So all the RCal data gets recorded before we start making changes in the instrument, so that we know what the initial settings all were in the instrument before we start changing things. So all of that data should be taken down before you start doing anything. Just to run you through what each one of these numbers in RCal represents. You have serial number, firmware revision, calibration date, the conductivity offset, conductivity scale, the temperature offset, temperature scale, compensation temperature reference. You have the compensation factor. You have the reference average. You have DA offset counts, picosiemens per meter. You have the DA slope, picosiemens per meter. You have the DA offset count Celsius. You have the temperature current low end, sample average, weighting factor. Next step is to go into calibration mode. So you type ***E to save your RCal settings. You want to make sure that N equals 1 and NREF equals 1 before going into calibration mode, because you want to do instant work. You don't want it to be waiting for 3 samples at a time. So then you type in ***C to enter calibration mode, SC to start taking numbers. Then you want to wait till at least 5 or 7 samples before you start taking the numbers seriously. The first 4 or 5 numbers are, can be anywhere. Okay, so once you've done that, you got your zero counts, your sensor counts, you have your conductivity counts, your temperature counts, and then this is your conductivity, temperature, and then compensated conductivity from the run screen. Okay, so now you're just seeing these other ones in front of it. So I'm going to take down all that information. So your zero counts, this first column here, should be between minus 15,000 and 15,000 right now, without anything going on. Okay? As long as that's the case, that's good. You can move on. This is your full scale counts. Those should be somewhere between 600,000 and 1 million. So you can see here, that's good. This right here is your sensor counts. Those should be between minus 15,000 and 15,000. Okay, that's your conductivity. So somewhere in between those two numbers right now, 4,000 is fine. This right here is your temp counts, and those should be between 400,000 and 600,000, unless you have an ATEX sensor, and then those should be somewhere around 250,000 or so. Okay, so if you have the ATEX version of the inline sensor, that number will be 250,000 roughly. Okay, but if you have the FM version, which is what we're calibrating, then this is in between 400,000 and 600,000 for this number here. Okay, and then this should be between minus 10 and 20. This column here should be plus or minus 20 to 25 degrees Celsius. And this should be plus or minus 10 to, minus 10 to 20 picosiemens. So all of those are fine, obviously. The next thing that you're going to do to check the functionality is you're going to take your finger and put it across the two electrodes like so, right? So that the inner electrode is being touched by one part of your fingertip and it's crossing like so. You can see that. See how my finger's touching the inner electrode and the outer electrode? That shorts out the sensor. And you should get something like 1179647, which means conductivity is over scale, which is putting out 2122 for conductivity. And that lets you know that the conductivity is working. And then if you hold the sensor tip with your palm like that, like just grasp it completely, you should see the temperature start to rise. You can see that the temperature counts are going down, so it's dropped down from 446,000 to 440,000. So that right there tells you that yes, the conductivity is responding and working, and when I release it, you see it drops right back down. And the temperature is working because it started going up when I was holding on to it and heating it up with my hand. Okay, so that's your functionality test for the sensor. So if you're ever wondering if the sensor is working or not, like say you're like, is the sensor working at all? You can always pull it out of the line and do this test with your finger and in air and see if the sensor will drop to 0 or if the sensor will go up to full scale with your finger across. That's always a good sign if the sensor is working or not, right? So as long as that works, you now have passed the functional verification segment. So now we need to verify that the voltage is calibrated, right? So we're going to, if you see here, fill out this sheet and make sure that the calibration of the voltage is correct, right? So that being said, the first thing we want to do is make sure that when we first turn it on, it fires up the full scale. So we have to cut the power. Wait for it to go all the way down. And then we're going to power it up. It reads 23.39. I don't know if you can see that. 23.39 MA, which is fine. And now we want to see that that drops down to somewhere around there, 4.84. That's fine. So what we want to do is calibrate conductivity equals 0 first. So we go over here, go into SRO, open mode. Then we want to go conductivity equals 0. And then we're going to check our voltage meter, which says 4.9, which is way above 4.00, is what it should read. So what we need to do is go over here and remove our serial port. Once we remove that, voltage meter is now at 4.05. So it's close, but it's not close enough for calibration. So we're going to put our serial port back on so we can communicate to the sensor. Go back over to our computer, and we're going to adjust the DAO down slightly to, let's say, 280. Save it there. And then we'll reset conductivity to 0. Then we have to go back and check again by, once again, removing the serial port. We've dropped the sensor down to 4.03, so we still need to go more. So reconnect the serial port. 278. Disconnect the serial port again. Almost there. All right. Serial port again. 4.01.
That's what I gotta check. I understand. Oh, I need those screws.
So we keep going and changing the DAO value till we get the desired value right there, which is 4.00 on the scale. And now that we have that, we record that down and we record the DAO value, which we got, which was 274. So to make sure we have that in, we hit save, check to make sure it's the right one. That's what's saved. And now we can go on to conductivity equals, in this case, the top end of this sensor is set to 1,000. Or actually it's set to 2,000. Equals 2,000. So the full scale of the instrument is 2,000. To get that, you set DAF to about 2,400 or above that. Generally, it's a little bit above that. As you can see, DAF 2422. If you want the max of the sensor to be 1,000, you set DAF to 1,200 and down from there. That's the scale. So you can see DAF here, and we have a voltage output of 19.99, which is right on the money, so we don't need to adjust the DAF value. But if you did want to, you could, DAF going up or down, adjust the value on the voltmeter. So that's how you adjust that if you need to.
Now we're going to calibrate and verify the voltage output of the JF-1A sensor.
So now that we have calibrated the conductivity loop for voltage, we're going to verify that, and that's the first steps in the calibration sheet, is to mark down the voltage output for conductivity and temperature. We started with conductivity, so we go over here, we type in conductivity. Conductivity equals 0. And then we go and we remove our serial connector. And we verify that it's still 4.00, which it is. So we write that down on our sheet. 4. Sorry, I forgot numbers there. So write that down on our sheet, 4.00. And our sheet tells us that's a pass. So we move on to half scale of conductivity. So we reconnect our serial port. Once we're reconnected, we go over here and we type in conductivity equals, so to set the middle range, we go conductivity equals, on this instrument, 1,000. And then that gives us 11.96, which 12 is about half of your 4 to 20 MA loop. So we go in over here and we type in 11.96. That's of course a pass. Expected output was exactly 12, but it's very, very close to that. So then we go over to full scale loop of range, which over here is conductivity equals 2,000. Then we go over there and we get a 19.99, which is once again right on the money. We type that in, and that's a pass. So we go over here, save all of that in there, and then just to check to make sure everything's working properly, it's always good to turn the instrument off at this point. Let it go all the way off. Turn it back on, and just verify that it goes full scale like that, 23.39, and then drops back down to about 4 point something. 4.84, so that's working properly. Now we can move on to calibrate the temperature loop. So to do that, you would disconnect power from the conductivity loop, put on the temperature loop, and you also need power either running through the serial port or through the conductivity port to have the instrument on while doing temperature. Conductivity can be powered just by the conductivity loop. The temperature loop needs power coming from either conductivity or from the serial port. So just keep that in mind. The next step in the process is to calibrate the temperature loop. In order to do that, we have to power up the temperature loop, which we did with this, and through the RS-232 serial input. So we go over here and we set the sensor to open mode. And now we're going to input temperature equals -20. And that should give us an MA of 4, which we're close to. So we're going to adjust it slightly. So TDAO is what you adjust. TDAO equals 292. Save it. Temp equals -20. And it went up to 3.99. So we might put up one more. TDAO equals 293 -20. Check rating. Now we have 4.0, so we'll hit save, mark that down, and then move on to the next, which is the high end. So then we need temperature equals 60. Gets us 20.04. TDAF is 83.7, so if we try TDAF of was 83.8. Then we want to do temp equals 60. I brought it down a little bit. .01. That's about as close as you're going to get. So mark that down, save it. And now we're going to verify that temperature works across the range. So temperature at -20, we get 4.00. Go to our little sheet here, and that's a pass. And over here we go temperature equals 20 and a 12.04. Go temperature equals 60, 20.01, and with that you have passed for voltage, and now we can move on to calibrating for temperature and calibrating for conductivity. But right now we know that both the temperature and the conductivity output is coming out of the sensor correctly. So if the sensor is reading 1,000, you know that the voltage coming out, the 4 to 20 MA signal coming out, is coming out correctly for 1,000. That's what we just did. Now we need to make sure that the sensor is reading the fluid accurately, which is the next step in the process. So for that, what we always do first is the temperature first. For that, you need the temperature bath and the temperature probe that we're going to sell you as part of the kit and all of this other equipment.
Now we're going to calibrate and verify temperature.
One of the things that we do is we measure out a 6-inch insertion depth for the JF-1A into the temperature bath. So now that we have JF-1A in the temperature bath, we have it hooked up to power. I have power running through the serial port. You won't. You're going to need to hook up both the conductivity and the temperature to power the sensor. However, you need the temperature loop powered up for sure. You'll get 2 power supplies with this kit, so just power both loops. They need to be running on separate loops, however. You can see we have it running. We have the temperature being measured here. It's 0.97 right now, and we need to let this soak for 30 minutes. So we come over here, and I reset the clock on hyperterminal. So you can see 53 seconds has transpired already. And what we do now is go star O, so star C, SC, and then we come back in 28 minutes or so and get the measurements in order to calibrate for temperature. It needs the soak for the next, half hour roughly. So once you've waited 30 minutes, you come back and you want to check what the sensor counts are in order to calibrate it. So you can see here the temperature probe is at 1.00 degrees C. So we plug that in here, 1.00. And now we're going to get the temperature counts. So over here and hit capital S to stop it from scrolling. And then we're going to highlight. I do it this way. I highlight 5 of them, copy them, bring them over here. And then I paste them into the graph, and then I just get rid of the extra data that was brought over with it until we get just the temperature counts. You can see it's just the temperature counts. The bottom there is the average. And now we're ready to get the high value in order to get our MT and BT values. So we gotta take the sensor out and change the bath over to 55 degrees, which gets it to about 59.6 degrees. So after you've soaked the inline sensor at 59.6 or somewhere very close to 60 degrees, generally just under that, like this, 59.6, you go over here and you'll write 59.60 in there, and then you'll go over here and you will grab the constants from this category, the counts, from this category here, which is the temperature counts. You'll copy those over, paste them in there, and get rid of the extra digits to get your M and T values, which you'll then plug into the sensor. Okay, so once you have your constants written into the sheet will help you with the math that we've already done for you, and it'll pump out a MT and a BT value that you're going to then put the sensor into open mode, star O, and then you're going to type out the MT and the BT value, and then you're going to save it into the sensor. Okay, once you've done that, you're going to go ahead and put the sensor back into calibration mode. We're going to verify that the sensor is reading the temperature correctly. So we're going to go over here and we're we're going to get our measurement from our temperature probe, which is still 59.60. So 59.60. And then our sensor's reading 59.6. And the raw counts are 58,102. And the current, to get the current value, we need to turn on our current meter. Set it to milliamps. And we need to go over here, hit stop. Star O to get it back to open. Star R. And then hit SC to get it to start collecting data. And it should go at 59.6. It should be just under 20 MA, which it is. 19.93. 19.93. And that is correct. So then we move on to the middle range, which means we have to take the sensor out of the bath and set the temp to 26 degrees and then soak the inline sensor for 30 minutes at 26 degrees and then come over here and fill out this middle section again to see if it verifies the temp at the middle range. And then we'll check the 0 again at 1 degree. So that's what we're doing. So now that the sensor has soaked for 30 minutes at the middle temperature, we check the temperature probe, we get a 28.1. So we'll go over here and we'll enter 28.1. And our sensor is reading 27.8, which is within the plus or minus 0.5 standard deviation. We have a temperature count of 394,780, which is good. Then we need to put the sensor into run mode to get the voltage. O, R, and then SC, and then we should get the voltage on the voltage meter in a second here. Once it starts taking samples. Okay, 13.6, which is correct. Record that. And now we're ready to verify the 1.0 temperature. But so far, so good. We verified the sensors working at 59.6 and 28.1 degrees, plus or minus 0.5, as you can see there at the top. So, on to the next. Okay, so now that the sensor is soaked at 1 degree, we can verify the 1 degree operation of the unit. So to do that, we're going to turn on our temperature gauge and check, which is 0.97. So we're going to go over here and on our sheet, we're going to type in 0.97. And our sensor's reading 0.9. which is well within the 0.5 variance allowance. The temperature counts are 679, 533, and when we go ahead and turn on our voltmeter, and we turn this into run mode, star 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 O, star 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 R, SC, and then once it starts taking a few samples, we can check the voltage. 0.9, and we have a voltage of 8.19, which is correct. We're not getting all the way down to the 0 for the instrument, which is minus 20, because the temperature bath doesn't go that low. So that's why it's not 4.0 MA, it's 8.19, because you're only at 1 instead of minus 20 Celsius. So that on the scale makes sense. So it's 8.19 volts, or sorry, MA, milliamps, and that is a wrap, so I generally save it here at this point, and then we move on to conductivity. So the main part here is we used a NIST traceable temperature thermometer to get our reference values, and then we were able to use the sensor counts to get a low point and a high point and do linear calibration across the 2 points, which when checked against various measurements comes out to be exactly what we are looking for. So therefore, NIST traceable temperature within 0.5 degrees Celsius, and that's all been verified. Now we can move on to conductivity.
The next step is to calibrate and verify conductivity.
So the first thing we do is we're going to calibrate and verify that this stick works in the field. Okay, so then we know that this stick is calibrated and verified. First thing we do is, with this version, you plug in the USB cord into your computer, be a normal USB port, and you go to your computer, and with this will come software. That software includes a program called StickCal. You open up StickCal. Once you scroll down, you can hit OK. Please ensure the is connected via USB cable and the ST is on. So we have to put the stick into the USB device. Once we've done that, we can turn it on. There you go. So it says push to sample. So it's in position. It says push to sample. Hit OK. Then we hit connect. And you see it's connected to the instrument now. And if you want to calibrate it, you hit continue here. Or if you want to validate it just to make sure that it is working, you hit validate. And for that, you'd hit continue because this was calibrated recently. So we're just going to validate it today. However, if you want to calibrate it, it's just the other button. Very easy to do. Does everything on its own. And with the SEF box, it would all be in the box right here, and you just hit one button or the other. So you wouldn't even have to connect it to your computer. It would all be in a self-contained box that runs all of this on its own and has a little LCD screen that gives you the information. But with this version, the USB version, it connects to your computer and prints it out via this program here. You can see the data's coming out. All of these values are good, which is why it's coming out green. If it was a bad value, it would turn red. All right, and if you want, you can print a copy of this that shows this handheld was validated. And we just pull the handheld out, and now we know we can go ahead and use this handheld to go ahead and calibrate that inline sensor, because this handheld is validated and verified that the calibration is right on the money. Okay, so now we can use this handheld to take measurements of these samples to know what the sample values are in order to calibrate the inline sensor. Okay, so once we are ready to calibrate conductivity, we'll have our fuel samples and our isopropyl alcohol ready to go. We have here is our zero fuel. We have our lab grade isopropyl alcohol, 99%. We have our conductivity of about 800 fuel. And we have our conductivity of somewhere around 1600 fuel in order to do a linear calibration again We're going to get a 0 value, a high value, calibrate with those, and then we're going to verify with all 3 that the calibration is correct. And we're going to use this as our verification device, as I've already shown you that we have verified this and or calibrated this before running this test. One of the first things you want to do is make sure that you clean the sensor tip off in your lab grade isopropyl alcohol. You want to do the same with the inline sensor. Dip in isopropyl alcohol, clean it off, and then blow off the sensor tip. Make sure you get inside the groove. Make sure it's completely dry. You don't want any of the isopropyl alcohol still on there. So we have our 0 to 10 picosiemen per meter fuel sample here, and we're going to get a reference measurement of that. So we'll dip the sensor tip in, stir it about a minute, and then push the sample. Wait for it to go all the way through the cycle. Try to stay still as possible. We have 0.9 for a reference measurement. So very clean fuel, 0.9 picosiemens per meter. We're going to go ahead and use that. Generally I take 3 measurements, but because this is a video, we're going to do 1. But generally you take 3 and then you take the average of the 3 and use that as your reference. So we have a reference of 0.9, and when we run our inline sensor in calibration mode, so you go open mode, calibration mode, we are at 1.8, 1.7, so we need to adjust our sensor down about 0.9 in order to get the value that we want. So to do that, hit stop. We'll check what our 0 is. We want to go down about 0.9 to get where we want. So we're going to change the 0 from -10 to -10.9. Save that in the system. And then we will go back into cal mode and check. And now we're getting values right around where we want to be. 0.6, 0.7, 0.7, and we're trying to get 0.9. So that is perfectly fine. 0.7, and we have a raw count of 8867. So we record all that down right there. We go over here and record our 0 value, say -10.9, which is a pretty standard 0 value to have. Now we need to get our full scale value. So in order to do that, okay, now we're going to get the high values for the inline sensor in order to calibrate the full range of the instrument. So we take out our trusty handheld meter, after cleaning it, of course. We're going to run it in our high sample. Get a value of 1611. I'm going to plug that in over here. 1611 for our value. And now we're going to run the inline sensor and see where it's at against that. Okay, so we've placed our sample on the sensor, and just make sure that the sensor tip is submerged so that you can see the holes in the sensor tip like that. And we're going to go over here and see what values we're getting. And we're at about 1570. So that tells me we need to adjust the inline sensor upwards. Stop. In open mode, full scale set to 1600, so we're going to go full scale equals, we want to go up about 50, I would say. Save it. We're going to go into cal mode and check to see if that's correct. We wanted 1611, and we jumped all the way up to 1641, so that might have been too much of a correction. So we're going to stop. We're going to go into open mode, which I already did. Go full scale equals 1625. So we do increments of 25 on the full scale. Save it. Back into cal mode and see how close we are. Looking for 1611-ish, and we're getting 1604, which is very close at that scale. 1606. So that's pretty close. It's as close as you're ever going to get. So 1606.1. And our counts are 924735. Which is pretty close to a million. When you're at full scale, it should be over a million. And I'm going to record our counts, which was 1625 for that, for the full scale constant. And now we're going to verify the sensor is working properly. So to verify the conductivity, we're going to use our handheld. We're going to run it in the eye verification fuel sample and get a measurement. $16.13. We're going to take this over here. We're going to get a sample on the inline sensor and verify. $1596.5, which is close enough. 919724, and you can see if it's within the 2% plus or minus 2%, it'll pass. If it's not, it won't pass. So that standard deviation is completely acceptable right there. And now we're going to record the current. So we have to go over here and go stop, R, and set this into run mode, which is ****O, ****R, SC. You can see it's actually, the conductivity is now up to 1603. So if I update this, it's even closer. And the current is now running at 1679. Now we need to verify the low range and then the middle range. Now we're going to verify the zero fluid. Now that we've calibrated the instrument, we're going to go ahead and get our zero fluid reference number. Say 1.6. So we plug that into our data sheet, 1.6. And then we're going to go ahead and run the fuel against the inlet. Put the fuel on the sensor tip. And go over here and we get our reading off the sensor. We gotta wait 7 counts. Okay, so our reading is a 0.8, which is a pass. And because we're in run mode, you can get the voltage, but to get the voltage at 0, you have to disconnect the serial port at 0. Not 4.9, it's 4.03 is your actual voltage. So when I put that back on, you'll see it flies back up. So your actual voltage at that is 4.03. And now we got to get the sensor counts. So we go into open mode, cal mode, and the sensor counts are 9194, but you gotta wait for it to adjust. Hold on. (9102), which is fine. It's all a pass. Now we just got to get the middle value to verify. Okay, now we're going to get our middle value. So we have our middle value fuel here. We use our reference instrument, the handheld stick. Go to get our value. Value of 834 picosiemens per meter. We'll plug that into our little chart, 834. And now let's get our numbers from the inline itself. Okay, so when we do that, we check it against it. We're getting counts of 826, 812, 794. So about 788. Now it's So we go over here and plug that in. 788.8, and our raw counts were 425.852, and then when we go into run mode, once we go into run mode, we got to get our voltage. The voltage is 9.63, which is right where it should be. And you can see now we have passed the conductivity, calibration, and verification. We've passed the temperature, the temperature, verification, and calibration. And the sensor has been verified and calibrated and now can go back into use in the field for the next year. And you verified it against NIST traceable standards, all with the kit that we can provide you. So if you would like to do this calibration yourself in the field, instead of sending your equipment to us to calibrate, you can calibrate the inline sensor on your own with the kit that we will sell to you. So just ask us for the JF-1A field calibration kit, and we will sell you all the stuff you need to do this on your own, except for a couple small things, like you're going to need your own temperature bath, you're going to need your own glass jars, your own fuel, and your own isopropyl alcohol. But all the others, and your own laptop. I'm not going to sell you a laptop. But all the other stuff that you need, like the voltage meter, power supplies, the cable to connect, the wires that connect to the loops from the power supplies, we will sell all that to you in a kit. Even the little thermometer will come in the kit. So all you need is a temperature bath, and this will come in it. You do have to annually calibrate this and NIS, and they'll come with a little calibration sticker on them letting you know that they are calibrated, and that way you have NIS traceability on those. So, and this, as I showed you, calibrates itself. So with that, you can calibrate these inline sensors on your own in the field.
If you've made it this far in the video, thank you very much for watching. We hope you found this tutorial extremely helpful. If you have any questions, please leave those in the comment section, or feel free to contact me, Fougere at D2Inc.com, or you can find more contact us information on the contact page at D-2.com. Speaking of which, you should visit our website and bookmark it because we regularly update it with new news. So if you enjoyed this video and you want more information, bookmark D2.com and visit it regularly. Hope you have a nice day, and thank you again for watching this video.